All right, well, welcome everybody. We got a couple more joining here, so I will maybe give it one more minute. Every time I start, somebody else jumps on. So, all right. Well,
Sorry about that.
no, it's all right. Yeah, it's a common enough thing in all meetings. I always either start a minute late or end a minute late. So, usually both. So, all right, well, I'm going to get going. So, welcome back, everybody. This is day 3 on our transmission line protection topic. So, I'm just going to dive right in. And what we're going to cover today is a recap of day 1 and day 2 at a very high level. We are going to talk a little bit more detail about some of the factors that impact reliability and the two reliability considerations, security and dependability, related specifically to distance protection and step distance schemes. And take a look at some of the other kind of unique scenarios and considerations that we might run into when applying a distance protection or step distance type scheme. And we'll also do a example calculation, kind of start to finish on applying a step distance protection package. So we'll do phase and ground protection. We'll look at loadability. We'll look at a few other things in our example, which will be a good intro to what is going to be in the homework assignment that, let's see if I can bring that up. I am somewhat late on developing, but I'll have this out early tomorrow with and I'll give you guys an opportunity to work through a step distance scheme and take a look at things. So just want to give you a kind of a sneak peek. So as we're going through the lecture today, you can kind of keep things in mind of what's coming up and what we're going to see in the homework. So I am going to have everybody go through and do a step distance scheme calculation and some validation in Aspen. So I'm going to send out this model here. This is one of the generic power company models that Aspen gives you with the installed their software. Very basic 138 or 132 kV transmission system. So I'm going to have you set this a relay step distance scheme at the terminal here at the Fieldale station, on the line between that station and Claytor over here. The kind of broke it into a few parts. We've got some background here in the first page. We're going to set zone 1 underreaching and a zone 2 time delayed overreaching phase and ground distance elements. We'll do some evaluation for loadability. We'll model them in Aspen and see how they respond, and that will be, the assignment to give you a feel for how line protection works and how you'd go about figuring out appropriate settings. So I've given you some Aspen data here, the MVA base, the station name, the line name in Aspen, so you can identify the correct terminal. And then the winter LTE rating, we'll talk about what that is later today. And then we've got the relay model, which is a Schweitzer 421, and we've got a CT ratio and PT ratio listed. So that's the data we'd need to be able to properly apply this by getting the rest of the data out of Aspen. So part 1 will be recommending a step distance zone 1 and zone 2 phase element reaches and delays based on the typical guidelines in class. So we've already kind of gone over the typical ranges of things that we would use. So you can use your discretion there at what you want to provide for margins and things like that. And I provided a place where you can, work out the math and make notes and whatever, and just provide the answers here. You can just, send it back to me however you want. Part 2 is checking loadability of the longest reaching phase distance elements. So we're going to talk about that today. Phase distance elements are responsive to load, so we need to make sure we're not going to trip our line off when it's heavily loaded. So we'll go over the criteria for that today. We'll move on to part 3, which is calculating the ground distance element, reach and delays, and the associated zero sequence compensation factors. So this is, again, something else we'll talk about in the example today, but that's just basically some, it's a factor that's applied to make it so your ground distance elements can be set similarly to your phase distance elements. So you'll probably, no surprise there, figure out that they're going to look a lot alike on parts 1 and parts 3. But you got to get those compensation factors right to make that happen. Part 4 will be modeling the settings you came up with in Aspen, and then taking a look at that RX plane and the RX diagrams to see how that looks, see how the loadability looks in the phase plot. And I've given you some guidance here on what to expect in that loadability plot. And then part 5 is probably maybe it isn't very complicated, but you get a few more subparts on it. It's actually testing out the coordination of one of your elements. I decided not to include both, but just take a look at your phase zone 2 element and see how does it coordinate with the adjacent zone 1 relays. So we talked last time about how zone 2 intentionally overreaches the remote bus. That means you got to coordinate it with your area protection. So in this case, if you're setting this relay here at the Fieldale, it's looking onto the line. You're going to need to coordinate it with the protection at this Claytor terminal and this other Claytor terminal, because those will be seeing, it'll be responding to similar faults for those cases. So you would do that by simulating faults on these lines, seeing how the protection on these lines responds, and then comparing that to the response of the relay that you're setting to validate coordination. So I got a few things on here of how to go about that, and we're going to go over a lot of this stuff today. Kind of on paper, and then I know you've had some experience with it. I guess I assume you guys have had some experience with Aspen. Have you worked in Aspen with other parts of the course?
Not much.
Not much. Okay.
Yeah.
So no one did this is Aspen, how to run faults and do things like that?
Yeah. I think it was rather basic, but
okay.
Yeah.
Well, we'll go through.
I'll let anybody else speak too if you feel better.
Yeah, I was
going to
say. I think we got an overview, but we didn't really have to use it to do an assignment so much. I don't think.
Okay. Well, you'll have a lot of fun with this because you'll be able to use it to do an assignment. And I'll try to spend some time at the end of the class here. To go over some of the basics of stuff. There's not a ton that you have to do here other than running a few faults and looking at the relay response. So I'll give, set aside 5 minutes or so, 5 or 10 minutes at the end to go over the basic things that you need to be able to accomplish what I'm asking you to accomplish. A lot of it you can just do on paper and come up with the right answer. And I've tried to set it up to remove some of the steep learning curve for Aspen, but if you all get really confused and don't understand it, we can spend some more time on it next class, and I can answer questions and show you how to do some of the stuff you couldn't figure out in Aspen. But it's a fairly user-friendly program compared to some of the other modeling software that's out there. So anyway, so we'll go through that. I just wanted to kind of give you that as a view of what's coming up today, so you could think about the types of thing you're going to be doing when we're going through the class. So, anyways, that's what we're going to be doing today. I guess any questions on the stuff from last week before we get going? So we'll have plenty of questions next class when you'll try to start working through the the assignment. All right, so just going to touch again on protection system objectives. Um, Reliability, it's a mix of dependability and security. It's a way we measure the not only that the relay is going to operate when we want it to, but the relay is not going to operate when we don't want it to. So we'll talk a lot about the two facets of reliability when we're going through some of these unique scenarios and challenges that you might want to think about in applying a step distance scheme today. Selectivity is, making sure we're tripping off the right things. If there's a fault on an adjacent line, you want to allow that protection to clear the fault before your relay does, because you don't want to trip off unnecessarily and remove a larger piece of the power system than is needed. Speed is obviously we want to clear things fast, but it's a trade-off because the faster you clear, the less information you're giving the relay to make a informed decision to make sure it's operating reliably and with appropriate selectivity for the case. Simplicity, there's a lot to be said for simplicity. It keeps things easily understandable, easily repeatable, easily maintainable. But oftentimes we're sacrificing simplicity in ways that we're trying to improve some of these other metrics: speed, selectivity, reliability. And then lastly, economics. Obviously, we got to pay for all of this. So those are kind of things we're going to be talking a little bit more about today. And I always like to highlight in every slide deck. So recap from yesterday or from Thursday. So we talked about a step distance scheme. Our step distance scheme applies multiple zones of distance protection or impedance protection, and each of the zones has a reach that's based on a percentage of the line impedance or some other impedance value that we extract from the Aspen model. So you can see here we've got a zone 1 relay, zone 1 element. It is set to operate instantaneously, and to do that we need to make sure it does not operate for any faults, and it doesn't have the sensitivity required to operate for any faults beyond the end of the line. So typically we're setting that at some percentage of the line impedance itself, because again, distance relays are set based on how much impedance down the line you want the relay to operate for. So in this case, it'll operate for faults roughly 80% of the distance down the line. Because that element does not cover the last 20% of the line, we also apply a time delayed zone 2 element. So we're setting that to overreach the remote terminal, again with some margin, so we can make sure, beyond any reasonable doubt, we're going to be able to operate for any in-section fault. And any amount we overreach is really incidental. We're not really using that as main protection for the equipment we're overreaching, but it's necessary to make sure that we're covering the full line plus some margin. With that, we do need to maintain selectivity. So we've got to check to make sure that the zone 2 element does not overreach the remote zone 1 element, because then we need to provide some additional time delays and coordination for the zone 2, because then you'd potentially have both of your zone 2s operating for a fault condition, which would impact your selectivity and reliability. And lastly, we've got a zone 3 element that's applied just for phase protection typically, and it's truly there as a remote backup. So it's going to be set with a longer time delay, and it's going to be set to look very far into the system to make sure we're overreaching and providing full protection for the next line off of the remote bus. And this is applied less these days than it has been in the past, but you'll still see them out there. And it's still a valid way to provide backup protection for the case that your battery system at the remote terminal fails, or a breaker fails at the remote station, or a relay fails. at the remote station, and that station isn't able to locally clear the fault, you're going to still need to clear the fault, but that's where the remote backup comes in. So I guess any other questions on this stuff before we move on? We're going to start talking about some of the reliability and security considerations for these schemes.
My name is Kyo. Would you look at my chat and answer to my question? Thank you.
Yeah. Sorry, I'm so you can calculate all the set points manually, but the a couple of them are graphically looking in Aspen, and you need to see the fault response and things like that. So there will be a couple that you'll need to use Aspen to solve. So and if I guess I'll leave it up to you guys. If you prefer not to use Aspen for this, I had a homework that I've done the last couple of years. I've done this that is all hand calculations, because a couple of years ago there was some issues accessing Aspen. I think I think if you have access to Aspen, it's a little bit better to use it, because it's easier to kind of graphically see what's going on and understand how the system responds to faults and things like that. But if you'd prefer to do the hand calculation version, that's a possibility as well. So
Thank you.
I guess think on it, and maybe we'll regroup on that at the end of the class. So
Thank you.
yep. So I wanted to touch on some considerations for your distance schemes. Again, reliability is that balance of dependability and security. When we start thinking about specifically our phase distance elements, we need to start thinking about loadability. So the transmission line's there to transmit power from one part of the system to another. Every transmission line, or really every current carrying piece of equipment in a substation, especially at the transmission level, has a continuous rating or multiple ratings that we can use to say this is how much power you can transmit through this device. And those are used in the operation of the system, so the system operators will know if they're pushing the limits of a specific piece of equipment. Obviously, the more current you have going through a conductor or any piece of equipment, the more heating you're going to have, the more stress you're putting on the component. And eventually you could have degraded kind of lifespan of that equipment, or it just outright failure if you overload it past those limits. So loadability is a really important thing. Utilities spend huge amounts of money to build transmission lines. It's millions and hundreds of millions of dollars to build transmission lines in some cases. So they don't want the relay to be the limiting factor in the loadability that they're able to get out of their system. So one of the key things we have to look at as relay engineers is how does the relay respond to load? So I've got a load region shown here, kind of this hash region over on the side here, and this is generally something that would be based on a MVA rating or current rating of a conductor or other piece of equipment on the line. And the load would typically be plus or minus 30 degrees. And really, it's usually closer to the resistive axis than 30 degrees, but that's usually the load range that we consider. And that kind of represents the 30-degree angle that you can kind of roughly see here that, the edge of the shape would make. So you can see here, in the very corner of this load region, we are overlapping our zone 3 element. So if the system operators were pushing this line to its absolute limit, the maximum current that you can put through it, or power that you can transmit through it, all the way up at that 30-degree angle, your load region is going to, your load plot or the apparent impedance seen by the relay for that load is going to be within this zone 3 characteristic. As we talked about last class, if you're inside the circle, that's the operate region for that element. So, even with the time delays and things like that, if you have your load in here, you would potentially trip this line off under load, and we can't. So we need to make sure that doesn't happen, because the last time you want your line to trip off is when it's heavily loaded, because the system's obviously at that point being pushed towards its limits. So to make sure we don't do that, NERC, which is a regulatory body that oversees utility reliability standards, has NERC PRC23. It's a requirement to validate loading and understand loadability of relay elements that respond to load. The main one we look at is our phase distance element. So NERC PRC23 has some requirements. You need to evaluate the transmission line relays. They do not operate at or below 150% of the highest seasonal facility rating for a circuit for the available defined loading duration nearest 4 hours. So a few things to pick apart out of there. One is we've got a margin of 150%, so we need to understand the loading capability of the line, and we need to apply some margin to that, so we're outside of that region. We also have the highest seasonal facility rating. So ratings vary by season. So we can push more power through the system in the winter because it's cold and it absorbs all the heat than we can during the summer. There's actually a new FERC order out that is having utilities switch to ambient adjusted ratings, which basically take weather and temperature readings throughout their system and adjust the system ratings in real time to constantly change what the facility rating is for a line. So again, you can push the system further and understand when you're closer to the actual limit, which is going to vary based on surrounding temperature. And then we've got this loading duration for the nearest 4 hours. So for any type of rating, typically it's going to be a value and a duration. The current you can pass through something for a shorter duration without damaging it is going to be higher than what you can do for a longer duration. So this is one of the typical ratings that we would use, is this 4-hour rating. They also have a requirement for very similar. We've got a margin of 115%, but for a 15-minute rating, sorry, I forgot to take the timing off of this slide. So we'd also have another way to look at it would be based on our 15-minute rating. And all of this is evaluated at 0.85 per unit voltage and a power factor angle of 30 degrees. So this is kind of their worst case scenario. Loading requirements is what we're looking at with this.
Hey, Brandon, is that the temperature dependent adjustments, is that kind of built in already, or is that going to be, is it a requirement? Is it already in house, or are people going to have to start buying the equipment to?
So utilities are still figuring that out.
Okay.
It is a requirement, but it's a very new requirement. Utilities are looking at it in a lot of different ways. So right now, how we've always done it is you have these winter ratings and summer ratings. Summer it's hot, so you can't push as much power through the system. Winter acts as especially up here in Maine, acts as a really nice heat sink to just absorb all of the heat out of the conductor, so you can push them a little further. They're are a bunch of different things out there utilities can do to meet this requirement. They're really still figuring it out. I haven't actually worked on one of these yet, other than from the relay perspective, we just need to know the worst case. We are not actively changing our settings over and over again based on temperature to avoid this loadability consideration. We just need to know the worst case. We cover that, and then then that's what we use. But there's some very especially on the control center side, the kind of back end of the utility operations centers. There's a lot of different ways you can go about doing it, either pulling meteorological data from from online sources, or measurements and things like that to validate it, things like that are possible ways to meet the objectives of that FERC order. So
Okay. Thank
it
you.
varies, but yeah, it's a new concern for utilities to then have to do it, but it's in the interest of being able to better operate the system and be able to maybe push it a little further than we can now by having better information, because we're able to, rather than just say, oh, winter and summer, just pick one of those ratings. We're able to actually say, okay, this is the rating today, or in the forecast of the next several days. This is what the ratings look like. All right, so when we want to do some loadability calculations, we've got this characteristic over here. This is the load region as expressed as the apparent impedance seen by the relay being at the origin here. And as the load gets bigger, the load point moves further in and closer to that origin. So if you have a line that's capable of carrying a very large amount of load, this characteristic's gonna kind of move closer to the origin. And if you've got a line with smaller conductors, you can't push as much power through it. Your characteristic's going to be out here. So the more load you're putting through your line, the more likely it's going to be overlapping with your impedance characteristics for your step distance scheme. So how do we go about evaluating that? We need a few things. We need to know the reach of the limiting phase distance elements. This would typically be your largest phase distance element, because the smaller ones are just smaller versions inside the same characteristic. We're going to need to know the loadability limit. So this is the point kind of that defines that circular portion of the load region. We're going to need to know the maximum torque angle of the line. So that's the relay's characteristic angle that it uses in its calculations, kind of defines how this circle, the angle of the circle in relation to the origin. And then lastly, we're going to need to know, the load angle. So this is that 30-degree point. And, luckily we can do some trigonometry. If you draw a line through a circle across the diameter, any 2 points hitting the circle form a right angle. So, you can calculate the impedance magnitude at the point at that 30-degree angle, and that becomes your loadability limit for that angle. That's how much the apparent impedance you would see for a load at that value. And then you can compare that to the impedance associated with your load region. So if your load region is a larger number than this loadability limit, that means that you don't have a concern with loadability. If your load region is in here, and now you've got this area that it is within there, the value you calculate at this angle is going to be larger than the load region, and that means you have a loadability concern and need to do something about it. So we've got some formulas here of how we calculate our load limit and loadability check. So first thing we do is we take that winter LTE, which is the long-term emergency or 12-hour rating, and that's the one that's nearest to that. That's that 4-hour winter rating, and you turn that into a current based on your line, your voltage and the MVA or megawatt rating of the line. You take your reach of the relay in secondary ohms, convert it to primary ohms, and then we're using that trigonometry function to calculate the reach of the relay at 30 degrees. So that's that graphic on the previous page. It's basically calculating the magnitude of the Mo characteristic, the impedance element, at that 30-degree angle. And you compare that to the 85.85 per unit. So that's one of the criteria, times your voltage. And 150% of your current rating that you calculated. And that represents that load region that you need to not operate for. So if your reach is less than your calculated load region, these are both impedances, that means you have no loadability issue. You're not going to have that overlap of the load region and your Mo characteristic. If it's the other way around and you don't meet this criteria, that means that you are going to have the potential to operate under load with the settings that you've proposed. ISO New England has a handful of other facility ratings. So your normal continuous rating is a 24-hour rating. You get a short-term emergency rating, which is higher than your 4-hour rating. It's a 15-minute rating. Then you get your drastic action limit rating, which is a 5-minute rating. And these are intended to give operators a chance to fix the problem before they have to make an operational decision to trip a line off that's heavily loaded and could potentially damage equipment. So what do we do if we have a loadability concern? We've done the NERC PRC 23 calculation. It turns out that we have we have a load region that is reaching into our impedance of the distance element. So what do we do to fix that? So there's a couple options. One is, if we have the ability to, we can shrink the element a little bit. All these elements, we had kind of a range of acceptable settings. So, maybe you could shrink it and still meet your other reliability objectives. But that's not usually the approach we want to use. Another would be to use a different shape of a relay characteristic. So one of the slides further on, we'll talk a little bit about some other types of shapes. There's a lenticular characteristic that's like a lens shape. You can kind of pull in the resistive reach of the element. There's quadrilateral elements that allow you to select your resistive reach, which you could use to move in outside of that load region. But by far the most common way we approach this is applying what's called a load encroachment element. And that's a setting inside the relay that blocks operation of any of your phase distance elements for based on a load impedance or load reach and angle. So you would set this, you'd understand where your load was, and you would set your load encroachment blinders to be slightly larger than that load region. And basically this kind of pink dashed area here represents the load encroachment blinder, and you can see it overlaps that load region. So the relay will block operation of zone 3 just for this small corner here that's within within the load region, and by blocking it, it makes it so that your element is now no longer going to operate under load for, based on that blinder characteristic. So any questions on load encroachment? It's kind of, or loading and the load considerations for that, I guess, before we move on to kind of next step. All right, onward we go. So I did reorganize and reorder this a little bit. I had the calculation example at the end, but I wanted to bring it up ahead so you can have it in preparation for working on the homework assignment. All right, so I'm going to apply. So what we're going to be doing is we're going to be setting. We're going to start with a phase distance calculation example. And we're going to have some data that we're going to need to know about our example. So we've got line data, and we're going to need the line impedance information. That's going to come from Aspen. Basically, you double click on the line itself. It pops up the window, and it's going to show R, X, R0, and X0. So your positive sequence and zero sequence impedance values. You don't have to worry about negative sequence. It's considered to be the same as your positive sequence. So we've pulled these values out of here, and this is what we have. We have R plus JX for positive and R plus JX for zero sequence. We have a line length characteristic. This is a 14-mile transmission line. And we've got some other system data. So the line is operating at 115 kV. The winter long-term emergency rating, so the 4-hour seasonal rating, is 300 MVA. And that's kind of the stuff we need to know about the line itself and the system. We also need to know a little bit about the relay. So we're applying a CT ratio of 240 turns. So it's a 1200 to 5 amp CT. And it's so that the overall turns ratio is 240 to 1. And we've got 3-phase Y-connected CT. So almost all the time, 99.9% of relay applications I've ever seen use Y-connected CTs, but where I didn't have a drawing here, I wanted to point that out. We've also got a PT ratio. It's a line to neutral connected PT, so it's from phase to ground connected. It's the primary winding. And the turns ratio is from 66.4 kV down to 66.4 volts. So we've got a PT ratio of 1,000. So that kind of frames the data we're going to need to be able to do our calculation. And this is very similar to the types of data you'll see when you do the example. All right, so first thing from Aspen, we have per unit values. So we need to get those from a per unit into a primary and then a secondary value, because the relay is seeing secondary currents and voltages. So generally, we're going to be setting our relay based on secondary secondary values. So kind of refresher back to power one here per unit. We're going to define our V base. Our MVA base is 100 MVA. That's a configuration parameter in Aspen. It comes with default as 100 MVA, and I've never seen a utility change it, but you can check in Aspen, but the model you're getting will have 100 MVA base. I'll point that out in the homework as well. And then we'll take those two and we'll calculate our impedance base. So this will be converting from per unit into primary ohms. So we do that conversion and we get a value here for, again, R plus JX for positive sequence and zero sequence quantities. And we'll take that and we're going to convert that into secondary. We'll do that by using our CT ratio and PT ratio. We'll take the positive sequence magnitude in primary times the CT ratio over the PT ratio, and that gives us our secondary impedance. And again, we're going to be setting the relay in secondary ohms, so we want to get everything over to that base. We can also calculate the angle of our line. So we've got the rectangular form up here. We can use math and get our angle in degrees. So positive sequence line impedance angle is 2.5 at an angle of 80 degrees. We can do similar on the zero sequence side and get 8 ohms at 70 degrees. And that's our secondary impedance that we'll use for setting our relay. So we go back to our philosophy. So we talked about our zone 1 and zone 2. Zone 1's an underreaching element, so we're going to set it to a percentage of the transmission line impedance. We just calculated that impedance. Our phase distance element is set based on the positive sequence impedance because it's responding to positive sequence faults. It's going to operate for line faults that are multi-phase faults primarily is what we're going to operate for with this element. So we're going to set our zone 1 Mo phase element. Z1MP is the setting in the 421 relay to 80% times the magnitude of our positive sequence impedance in secondary ohms, which you recall was 2.5 ohms. 80% of that gets us a nice round 2 ohm secondary as our reach for our zone 1. And we can do the same thing with our zone 2, and this is our overreaching element that is going to reach past the end of the line, and we're going to apply some margin to that. So we're going to protect 100% of the line plus some more. And typical values range from 120% to 150%. So in this case, we're going to use 120%. And again, we're just applying that factor to our zone, our positive sequence impedance magnitude of 2.5 ohms. So we've now got our zone 1 setting of 2 ohms and our zone 2 setting of 3 ohms. Because zone 2 overreaches the remote bus and it will operate for faults past that, we want to delay it so that it gives the protection at the remote bus or the adjacent lines some time to operate. So we'll apply a 20 cycle delay to that element. So the next thing we need to do is we need to make sure that the element we just set is not going to overreach the remote zone 1 elements. So if you recall that step distance diagram we looked at last time, was kind of a staircase and compares operation of one relay to another. We want to make sure for any fault condition that the relay we're setting can operate for within that zone 2, that we have some amount of a time delay between that zone 2 and how the protection's operating on the other side. So because we've set it with a 20 cycle delay, we've got plenty of margin if the protection operates instantaneously. But if you start operating and your zone 2 overreaches the remote zone 1, meaning that now you're coordinating between your zone 2 element on this line and a zone 2 element, let's say on this second line, you've lost that coordinating margin. So you're going to have to either reduce your reach or increase your timer to provide some timing between those two cases. So we're going to do that by simulating some faults in Aspen. So we'd go to this line 2 and line 3, and we'd run faults along the line at an increment. So let's say every 1% of the line, we're going to run a fault until the remote zone 1 stops operating. Then we know that's when this relay is going to stop operating instantaneously, and it's going to start operating on a time delay. And we can go in Aspen and we can see what is the apparent impedance that the relay that we're setting is going to see for that fault case. And that's what I've got shown here. So for the apparent impedance seen by line 1 relay at the line 2 zone 1 boundary with line 3 out of service. So we'd look at this both with all of our lines in and with any single contingency. So we'd remove this line 3 from service. We're going to see 16 ohms primary, and we'll see that value at this line 1 relay. And we can convert that back down to secondary ohms. And you can see that we've got 4 ohms secondary. Now, if we look back to our settings on the previous page, our zone 2 is set below that, which means it's not going to respond for that fault because the fault is further away than the relay is set to reach. And we do the similar thing to look at the apparent impedance that the line 1 relay will see for a fault at the end of the I think this should say line 3 boundary at the end of that zone 1. And we get a similar apparent impedance in primary ohms. We convert that back to secondary ohms. But because in both of these cases, the zone 2 reach for the line 1 relay is less than the smallest apparent impedance for faults at the end of those zone 1 boundaries, with an outage consideration and all that, we've properly coordinated our line because any of the cases that our zone 2 is going to operate for are going to operate instantaneously based on the zone 1 element of these other lines. And this is one of the things that's a lot easier to see graphically in Aspen than it is to, just look at numbers on a slide here. So maybe we can take a look at what that looks like for how you're going to get these apparent impedance values, how you're going to figure out where the where the end of that element reach is compared to other relays in the surrounding system. Any questions on this stuff? This is probably one of the more conceptually challenging ones to go over. You really got to just play around with the model and to understand it. But any questions before we move on? Okay, great. All right, so next thing we're going to do is we're going to check our NERC loadability. And again, this is using the same equations we had on the previous slide, a few slides ago now. But the first piece of information we're going to need to calculate our current rating of the line is our winter LTE rating, or the 4-hour rating of the transmission line. We use that and our voltage rating to come up with 1,500 roughly primary amps as our line rating. And then we're going to calculate the two sides of that comparator to tell if loadability is met or not. So the first one is calculating the impedance characteristic, or the impedance reach of the relay at 30 degrees. I guess that's the second one down here, where you're taking your longest element, in our case, the zone 2 element, and finding the reach of the relay at 30 degrees, which is just about 8 ohms. And then we're going to compare that to the maximum possible setting we can apply without having a loadability issue. So this is really that impedance that defines that load region that we need to apply. We've got our 85% factor. We've got 150% margin on our current rating that we calculated. And that results in just under 25 ohms primary. Because the relay reach at 30 degrees is less than the maximum possible relay reach based on loading. Because that's true, our loadability is met, and we don't have to do any load encroachment blinders or anything like that to apply this protection. So the next question is, what about ground distance settings? So ground distance operates on zero sequence impedance, or zero sequence measurements, currents and voltages. Zero sequence currents and voltage is what the relay uses to calculate and operate the ground distance element. But the convention for a long time has been to, rather than have the same type of calculation that we'd go through when we calculate the zero sequence impedance magnitude and apply the factors to it, the convention for as long as I've been doing this is that we apply a scaling factor that allows us to set the zero sequence elements with positive sequence values, and then provide the relay a factor that basically compensates for those and switches them to their equivalent zero sequence quantity. So we do that using this K factor. Different relay manufacturers have different ways of doing it, but largely we're taking the zero sequence value, and we are doing some way of comparing that to our positive sequence value. So in this case, we're doing our Z0 minus Z1. This angle should not be there. I've got to clean that up in the slide. Divided by 3 times the positive sequence. So zero sequence minus positive sequence over 3 times positive sequence. And this is done, and it'll end up with a magnitude and an angle, and that we'll program in the relay that tells the relay how to take the positive sequence impedance setting we've provided it and turn it into a zero sequence value. Basically, it converts it internally in the relay. So for our ground distance settings, the reaches become very easy. Your zone 1 is ground is equal to zone 1 phase at 2 ohms. Zone 2 ground is equal to zone 2 phase at 3 ohms. And then we need to calculate this K0 factor. So we take positive sequence impedance, 2.5 ohms at 80, and zero sequence impedance of 8 ohms at 70 degrees. We plug it into this formula here, and we get this K0 factor that we've got 0.741 at an angle of negative 14.48 degrees. And the two settings that we'll put into the relay for that would be the magnitude and angle independently as 2 separate relay parameters. By doing this calculation, it keeps it very easy to compare ground and phase reaches, because you can see that, okay, the phase is set at 2 ohms, the ground is set at 2 ohms. They're going to operate for a similar distance down the line of 80% of the impedance. Same thing with the zone 2 element. And that's largely all the calculations and evaluation we need to do to prove out this element and set the relay, configure the relay to operate for this step distance scheme. Any questions on the calculation example? Okay. All right. So doesn't seem too bad, does it? You do some per unit conversions, you get it into secondary. You have a large orange cat that refuses to not be on your lap. So it seems like it's really not too bad. Well, it's a simplification. That is the analysis we do, and that's the calculations we do every time we do one of these applications. But there's a lot of other things we have to consider with line protection. And what are some of those other things you might have to think about? So we'll touch briefly on these. I do want to leave some time at the end here to do some demos and show some stuff in Aspen. But I did want to touch on some of these things of, what are some things you might run into? So a few things here. I think I've got a slide for each of these, so maybe we'll just go through the slides in the interest of time. So your line length is going to impact your the ability to apply this scheme. So if you have a really short line, there's really not going to be much electrically different for a fault that's close into the line versus the end of the line. We kind of talked about that a little bit when we were talking about, why do we have to set zone 1 to 80%? Why can't we set it to like 99%? It's because there's going to be some variability in your measurements. You're going to have some errors in your relay calculations. You're going to have errors in your CTs. So same can be true if you have a very short line application. Transmission lines can be 50 miles long, 80 miles long, 100 plus miles long, but they can also be half a mile long. And what are the considerations you might have to think about when you have a really short versus a really long line? So one of the ways we evaluate this, because physical distance isn't always a good representation, we really want to know electrical distance. And the way we measure that is source impedance ratio. And basically it's comparing the Thevenin equivalent source impedance to the line impedance. And if that value is very low, like less than half an ohm, or less than half, because it's a unitless value here, that means we have a very long line. We've got a lot of line impedance compared to my source impedance. But if it's above 4, it's the other way around. We've got a lot of source impedance compared to our line impedance. And that'll impact our ability to set an element that can differentiate between a fault really close in on the line and the end of the line. Because ideally, like we talked about in general with an impedance as a unit or as a operate quantity for a relay, you want something that for different faults or different scenarios has very different values, and you're not going to get that in a short line. So this is one of the things we evaluate in our short line applications, especially very short line applications. We may need to pull back the maximum reach of that zone 1 element. So we gave that typical value of, we can set it to 80% of the line. But if you get a really short application, you might need to adjust that. If you have an SIR of 25, and this is just a typical guideline from a really great Schweitzer paper called Transmission Line Settings Calculations Beyond the Cookbook. There's 2 parts, and it's a great primer on transmission line protection. But anyway, this is a table out of that paper. If you have a really high SIR 25, you go over and you might want to consider limiting your reach to 50% or so, because the electrical quantities you're going to see for a fault at 50% are not going to be that much different than a fault at the very end of the line. So you need to be able to differentiate between that. Mutual coupling, we touched a little bit about on day 1, that, if you have multiple lines in the same right of way, you can have some coupling of fault current from one line onto other lines. It'll impact the behavior of the faults, particularly with zero sequence currents. Those are unbalanced currents, and the way they, balanced currents kind of cancel themselves out in mutual coupling. So we kind of largely ignore them. But for unbalanced faults, this becomes a much bigger concern. And what you'll see with that is if you apply ground distance protection on a heavily mutual coupled line, maybe a parallel line between 2 substations, the apparent impedance that you see for a fault with the system under a normal condition versus with the mutual coupled line out of service or grounded is going to shift quite drastically based on the impacts of that mutual coupling. So if we do have mutual coupling on our lines, we need to do a lot of fault analysis to make sure that the relays are going to be operating reliably.
Hey, Brandon.
Yeah.
And this might be a dumb question, but I remember years ago in my undergrad that do they kind of swap the lines over after a certain distance to deal with that, or is that completely different?
No, they do. Yeah. So it's they'll if you have a long transmission line, they will transpose the conductors so they're in different, if they're a vertical, you've got your three conductors oriented like this, they'll actually go in one of the, they'll have a structure here that, the conductors will go up to it in one orientation, and then they'll cross over and go in a different orientation to the next tower. Probably wouldn't look like that, but
Yeah.
it changes it so that as you go down the line, you don't end up with imbalance in your self impedance. And you can do the same thing with adjacent lines as well. If you had a double circuit tower configuration, you could do something like that. Largely, we assume in relaying that, or most protection and modeling, that our lines are continuously transposed for the purpose of self-impedance. So the impedance of phase A isn't going to be different than phase B, than phase C.
Okay.
But really where the mutual coupling comes in is when you have the two lines that are physically sharing that same right-of-way, and you can't really transpose those in a way you're not going to have any mutual coupling impact, because it's not just that you have two lines that are with the self impedance. You get three conductors that are all have roughly the same current going through them for a multi-phase fault, and it kind of balances out because they're all balanced. When you have two lines, it might be that one is sending fault current in one direction, the other one's supplying fault current in the other direction, or a different magnitude, and that coupling that's really where the mutual coupling consideration comes in, is when you have two different lines that are seeing different electrical parameters physically close enough that you have that mutual coupling effect.
Okay. Thank you.
So we're running a little short on time here. I'm going to flip through just a quick few things. I got a bunch of notes on here. You can certainly read through them. If we have some time on next class, maybe I'll go through some of this stuff in more detail. So in-feed is when you have a source in the middle of your line. It's going to impact the impedance your relay sees, and so it's not really going to be exactly lined up with the line impedance itself. So the power system also has some dynamic responses, and power swing is one of them. It's oscillations between when the system changes and the mix between generation and load changes. Sometimes due to a fault, it can your power flow through the system is going to swing outside your normal load region, and can, similar to load, that impedance that it's seeing during this dynamic response can get inside your protective elements. It doesn't last long, so we only care about it for instantaneous elements. And you got to make sure it doesn't operate for that. In the last 4 or 5 years, NERC came out with PRC26, which gives some screening criteria that says you got to evaluate this to make sure you don't your protection doesn't trip off for one of these stable power swing events. We also have resistive faults. I kind of showed this in Aspen the other day. If you have resistance, it pulls the apparent impedance that your relay sees outside your characteristics. So even though it's only halfway down the line, if there's enough line resistance, it'll impact the measurement quantities the relay sees and can pull it outside of your value, outside of the operate characteristic. And then lastly, we've got some other impedance characteristics. So I mentioned the quadrilateral. So this kind of box here is another way you can set up your relay. Gives you a little bit more control to provide that resistive fault coverage, because you can shape your characteristic and make it wider to cover a bigger area. If you do this on a phase element, that's also pushing you closer to that loadability area, so maybe might not be what you want to do there. And then another type of characteristic is a lens. So this is that Mo characteristic, but you basically are squishing it in, so it turns into kind of this football lens shape. And you can do that to avoid load. You could do that to avoid that power swing region and things like that. You need to change your settings, but almost all the time everybody uses Mo characteristics. Sometimes you will see these quads. I think I've only applied 1 or 2 lens characteristics ever. So So in conclusion, we got a lot to think about with line protection and step distance schemes. We got a lot of flexibility with modern relays, so we can kind of evaluate and set them up in a way that we're going to be able to meet those objectives. We're going to maintain loadability. We're going to be able to maintain dependability and security. And the typical settings calculations aren't too bad. It's really not too complicated to understand how to set your relay. But there are exceptions to that. There's some of those unique scenarios and things to look out for short line applications, mutual coupling considerations, um, power swing, stable power swings, and things like that that you need to consider and think about, but are kind of more advanced topics um, for uh, transmission protection. So real quick here, I'll bring up that out. All right, so we're going to be working on this relay over here. This is the one we're setting. I set up these relay elements in here that are set up in a way that you'll be able to add your protection set points to them when you calculate them. So you're going to have the settings in here for, Z zone 1, Mo, ground element, and you'll put in your reaches here. You'll fill in your line impedance data up here. Delays down on this Z1G and Z2GE settings, and then here are your K parameters, those zero sequence compensation factors. So it's kind of set up for you to add your protection to it. When you do, you will be able to then see your protection on the RX diagram and see how it responds to various faults. The phase will be set up very similar to this. Won't have the zero sequence compensation factors. It won't care about zero sequence magnitude, so you won't have to put that in there. But that's largely what you'll use to model these faults. And you can get to that just by double clicking on your relay group. And then double clicking on the relay element, it'll bring up the data there. And I'll send this model over. So I think I set this one up, maybe. All right, so yeah, I do have something in here for this remote relay. Let me try this. Okay, there we go. All right, so if I want to see how this phase relay responds to faults, I can run some faults on the line. To do that, you click a location. It's typically in relation to a line terminal. Right click and specify a classical fault. And then you can go in here and choose, if you want outages, if you don't want outages, what type of faults we want to look at. And you can also put them by percentage. So it might be interesting to go in here and just put in every 10% of the line. If you hit this auto sequence, it will put 10% over this range. So it'll do a bunch of faults for us. For phase faults, we can just run a three-phase, three-line to ground fault, and we will run that and see what it is. We're going to get some information in Aspen. It'll show us a description of the fault. So this is the fault at 90% of the line, and it shows you which elements operated. Shows you the response time of the relay, so the delay. And it shows you the apparent impedance for each phase plotted. So we've got apparent impedance plotted here at 5.96 ohms. That's ohms secondary, and it gives you primary ohms in the parentheses afterwards. And it gives you the angle that the impedance was as well. So this is that apparent impedance for this fault that the relay sees. We've got our settings up here, and we've got our line impedance here. So this might be a great way to check your hand calc for your secondary ohms and line impedance. We'd be looking here to check that. And then you can use these arrows up here to navigate between different faults. So you can see at 80% of the line, we're still operating within zone 2. And then when we step into 70% of the line, we're operating within zone 1. And if you just look at the numbers here, we get 4.63 ohms as the apparent impedance, which is less than 5.10, which means we're inside this characteristic. It's a little more complicated than that because you got to factor in the angles and stuff. But this will show you how that relay is responding to those faults. And you can then go through the whole list of faults here. I don't know, do I have another? Well, let's see what happens. Okay, so if we want to add an element, actually let's do add a load region. So if we add a load region, you can click add. It's not letting me add. I think it's just interfering with my screen share up here. Add a load region, and you can specify what it is. Let's say this one is 500 MVA, nominal voltage, power factor, that's that load angle, and the per unit voltage for the load. This is the MVA at 1 per unit voltage, which is what it's rated at, and this is what it's actually showing, which is the 0.85. And we're going to show the load region. So you can see here it's added the shaded region here. If you need to change that, you can go up and edit your load region and say, oh, what does it look like if I put 60? Yeah, it's all much smaller. But if I go in and edit my load region, I can say, okay, 600. Okay, well, now I got a loadability issue. So you can play around with that to understand the loadability calcs and see how those relate. If you want to, you can also add another relay to this characteristic. So if I went to, I don't know which one this is, but it's probably this one. I think it's this other element there. You can add that, and that's going to be, I think, this relay here. So it's NV phase 1. So that's this relay element right there associated with this line. So if I wanted to, first thing, just looking at this graphically, you can probably see that the zone 2 here is overreaching this zone 1 element, because graphically the Mo characteristic with zone 2 is past the zone 1, which means in this area in here, potentially we'd have to coordinate our zone 2 timer with this zone 2 timer, whatever it happens to be set at. But if I wanted to find out what is that apparent impedance for the relay I'm setting at that zone 1 boundary, the best thing you can do is specify a fault, put it at 1%, we'll clear the previous results, and we'll start at the origin. So this is the fault right here near this terminal. You can see that the red relay is operating on zone 2. The apparent impedance is lower than the zone 2 boundary. And I can then move this fault up, and you can see until we hit the point when the remote relay is stopping to operate. I don't know why. Why did that do that? Saying it's operating within the zone 1. So maybe that. But anyways, you could go in here and see where this element stops operating. Oh, okay. No, I was looking at the wrong one. Okay, so we've got the two apparent impedance plots here. One is the line relay that we are working on. The other is the line relay that we're evaluating here in black. So if we keep going, we're eventually going to hit the zone 1 boundary, and you find that when this says zone 1 tripped for one fault, and then the next fault it says zone 2 tripped. So that's the point, right at the boundary of the zone 1, and in past this, we're going to coordinate zone 2 and zone 2. So that's how you'd find that value out of Aspen. The rest of it should be fairly straightforward to find. You can find the line impedance values by clicking on the line data. The relay values are in here. If you do need to specify a outage for a line, you can either do that this way. You can go in here, specify the fault, put an outage on it, and then actually I'll do this one. Specify a fault with an outage, and we'll just put a line in fault with an outage. Hit simulate. Three phase. It's going to give you options for which lines to outage. Select this other one. It now shows that line out of service, and you can evaluate it for a normal scenario or a line out scenario. So that's basically, I think, all the tools you should need to be able to do this homework assignment. But I'll spend some time on the next class going over any questions folks have, or you can always email me and I can get on a quick call to, answer questions on Aspen or clarify the question or anything like that. So I'll get the homework out here, maybe not tonight, but certainly tomorrow morning. Yeah, then we can come back with questions on Thursday, and then we'll talk about pilot protection and line differential schemes and some other more advanced line protection topics. So, all right, I appreciate everybody holding on for a couple extra minutes. One more thing to note, I am on site, going to go do a site tour of the new HVDC terminal in Lewiston for the new high voltage DC line that's coming in from Canada. I should be back for 5 o'clock, but if I'm a few minutes late or I'm looking like I'm going to be a few minutes late, I'll send something in the chat here and I'll let you guys know, but I will be here. It just might take me a few extra minutes to get here if I end up running into a delay of some sort at the site. So appreciate everybody hanging in there, and just I guess any questions before we wrap up?
Would you look at my chat, please?
How to link the protection faults and the diagram? Okay, yeah. So when you run a series of faults, so if I put a fault value here, a line in fault with no outage, and then maybe I select a couple other faults. If you clear previous results, it clears out all of the results, and then the only 3 faults you'll be looking at will be these 3 fault scenarios. And if you hit simulate, so there's a couple ways you can relate the diagram to the figure. One is it provides this fault description. It says the fault you're looking at on the figure is a line in fault on it, and it gives this specific line, the Claytor Nevada line. It tells you it's a 3-line to ground fault, so you can know what fault type it is. And you can see that graphically somewhat on here as well. So here's that line, Claytor to Nevada. You can see that the fault location represented by the X is at the end of the line. And then it's a little bit harder to see, but you can tell it's a 3-phase fault because it's showing you positive sequence parameters. If you want more data, you can click this TTY window, and it will give you a much more data about the fault and the description based on which one's displayed. And then you can scroll through any of these using this navigation. So if you move over to the next fault on the one line, it also moves you to the next fault on the RX diagram. And also moves you to the next fault on the TTY window with the additional data. So they're synced together. So, usually I'll have them up on one screen like this, and then I can see graphically where my fault is. Bus fault at this bus. And then I can see the description here. And if I need the more data, I can go back here and look at the detailed window that gives you a whole lot of extra information about the fault and its evaluation. And how to access the file. Yeah, did you have a follow-up on that?
Yeah.
Okay, so the other part was how to access the files. So I will send this a one-liner file along with the homework. I understand the university license is up to 50 buses, so this one should fit nicely into it. It should run just fine on your Aspen one-liner through the university. If it doesn't, let me know, but it theoretically should. So. But I'll send this file along, and it'll have all this stuff set up for you, and all the other details you'll need is in the homework assignment. So it'll be a good opportunity if you haven't had a chance to work in Aspen and see how the relays respond yet. This is a great way to really understand this stuff in a more hands-on way. This is how we do it as practicing relay engineers as well. So
It will be in Brighter Space, or it will be in somewhere else? The file, I'm talking about the file you are going to.
I'm sorry, I didn't follow the. As far as where the homework will be posted, I'm going to send it to Paul, and he is going to put it wherever the homework is going. I've got a link to the Google Drive folder. I don't know if that's where you typically would get assignments, but I'll probably put it there and then send it to Paul and see where he wants us to put it. I don't think I have access to any of the other systems. So.
Okay, thank you.
Okay, great. And as far as a due date for the homework, you can have the next couple weeks whenever to get it done. I'll try to figure that out and put it in there, but I'll give you some time. I want you to have certainly the next 2 classes to come back with questions and things like that to make sure you're able to get past any of the hurdles with using Aspen and figuring out the questions, but certainly reach out to me on email or anything if you have any questions on it. So, I'll say probably 2 weeks from today for getting the homework back to me, and I'll grade it and get the feedback back to Paul. So, great. Well, I appreciate everybody hanging on a little extra here and going through this stuff. I'm glad I was able to do a bit more in Aspen with you. I'd, for some reason, thought you already had some Aspen experience with some of the previous sessions. But it's a very powerful tool. It'll be good to get some experience with it on this, and it's a great way to really be able to more visually understand the line protection you're applying. So appreciate it, and yeah, everybody have a great rest of your day, and we'll meet up again on Thursday, and I will let you know if I'm going to be at all late for the Thursday session based on getting back from my site visit up in Lewiston. So. Take care, and we'll talk again Thursday. Thanks again.
Thanks, Brandon.
Thanks,
Thank
Brandon.
you.
Have a good one.
Thank you.